Today, we're going to talk about the second law of thermodynamics. And believe it or not, pretty good understanding of the second law. But our full understanding, even though this law was developed a couple hundred years ago, or 150 at least, it's not until relatively recently that we really got a handle on why it works the way it does. And here's what the issue is. If you look at what the second law does, it tells you which way energy will flow. There's nothing in classical mechanics, nothing in classical mechanics that'll tell you that if I have a system at a higher temperature and another system at a lower temperature, and I bring them together, why the energy goes from higher to lower. Classical mechanics does not tell you why. Okay? Why is that? Because for every trajectory in classical mechanics that goes from one place to another, there's an equally valid trajectory that goes the other way. For example, if I have a particle moving around in a circle in a clockwise direction, it's equally likely to go in a counterclockwise direction. Both of those trajectories are valid. Classical mechanics says they're okay. So what is the issue? The issue comes down to probabilities and initial conditions. In other words, the kind of arrow of time of thermodynamics is all based on the idea of initial conditions being somewhat different in different cases. So for example, if I start out all the molecules in this room in one corner, what will happen? What will happen to those molecules? Are they going to stay there? What's going to happen? They'll disperse. They'll fill the room. So when they fill the room, it goes from there to there. All right, so the gas molecules in that corner will fill the room. And I can guarantee you, I would bet you $1 billion NT that that's going to happen every time. But right now, the molecules are dispersed around the room. There is nothing in classical mechanics that says that I can't reverse all the trajectories and have them all go to that. All the molecules go back there. Like taking a movie and running it backwards. There's no reason in classical mechanics, there's no reason why that's not a valid situation. So why doesn't it occur? It occurs because the probability that it could occur is so tiny, right? It could occur maybe in billions and billions and billions and billions of times the age of the universe. But it's not going to occur even in the age of the universe, or 10 times the age of the universe, or 1,000 or 1,000,000. All right? In fact, I don't even know how many billions I have to say before it might occur. Might occur. So somehow, thermodynamics built in a law which takes this idea into account. And that law involves the idea of entropy. So that's what we're going to get to today. All right? So the key idea is physicists knew they needed to add something to thermodynamics to figure out which way energy will flow. And they came up with this brilliant idea. They said, let's invent a new quantity. Every system has this quantity. You have it, I have it, this chair has it. Everybody has this quantity, and it's called entropy. So they just make it up. So we have a new state variable. And this word state is important, called entropy. We usually use the letter S. Okay? It's almost always used, capital S. So that's entropy. And it basically has two important properties. Number one, S is extensive. Everybody remember what that means? That means the entropy in this room is the sum of the entropies of each of you, plus the entropy of the air, plus the entropy of the tables, plus all the chairs, right? You just add them all up, okay? It's like volume or mass or energy, extensive, right? And the second, and this is the most important, is in a closed, isolated system, the entropy always stays the same or increases. So if I have an isolated system, so nothing goes into it, nothing comes out. No energy, no particles, nothing. It's a closed system. The entropy either stays the same, which means it's at equilibrium. So over time, it's just sitting there at equilibrium, or it gets bigger. All right? And we'll do an example where it gets bigger, where it changes. Okay? And this second thing here, this is called the second law of thermodynamics. The second law is basically that. That's one way of formulating it. There are two or three others. But this is the way that would be useful for us. Okay. So this is a key idea. And it's unbelievably abstract. I mean, the people who invented it had no idea what entropy was. They just made it up. They didn't really know how to measure it. All right? We'll show you ways of calculating it from measurements. All right? But they really didn't know what it was. They just knew we needed something. All right, now let's take this and we're going to develop what I call a thermodynamic definition of temperature. Remember, we don't really have a definition of temperature yet. We have something from kinetic theory, but that's not a definition. And we have some things from measurements, ideal gas laws, and things like that. But we don't really have a definition of temperature. So that's what we're going to get. Okay, so here's how we're going to do this. So we imagine a closed system, just like we asked for, a closed, isolated system. But it's divided in half, or in two pieces. Doesn't have to be a half. So here's our system. Oops. And we divide it into two parts. All right, so one part has N1 particles, has an energy E1, it has a volume V1, and it has an entropy S1. The other part has N2, E2, V2, S2. All right? So it's completely defined. But it's not necessarily in equilibrium. This part is not necessarily in equilibrium with this. All right? So these two start out in any state with those numbers. Okay? Now, we allow one thing to happen. We allow energy to flow from one system to the other. We don't know which way it's going. We really don't. And just because E2 might be bigger than E1, that doesn't mean energy is going from here to here. Right? Because this could have a larger volume, larger number of particles, etc. Okay. Now we're going to apply the first and second law of thermodynamics and get out a definition of temperature, or at least motivate a definition of temperature. All right. So from the first law, if the energy flows from here to here, then this energy will go down, that'll go up, but the total change in energy is 0. Right? So we have delta E equals delta E1 plus delta E2, and that's got to equal 0. So that implies delta E1 equals minus delta E2. Now, nothing else changes. N1 and N2 don't change. They're not allowed to go through this barrier. V1 and V2 don't change. This barrier is fixed. Only energy can go through. All right? So the second law says that delta S equals delta S1 plus delta S2 is greater than or equal to 0. So that's the second law. All right? So it's a little different than the first law. There's that greater than sign there. Greater than or equal. Now we can write this in a slightly different way. We can say, let's take the derivative of S1 with respect to E1, and then times it by delta E1. This thing here is the same as that. One way of seeing that is this little delta E1 is essentially the same as that delta E1, and then you have delta S1 is there. Okay? If you don't like the partial derivatives, you can use regular derivatives. But hopefully you've seen this kind of thing in calculus. And then I could do the same for delta S2. So I had ds2 dE2 times delta E2. And that's got to be greater than or equal to 0. Really important that you understand this right now. This is the key. What I'm going to do next is pretty easy. This one I actually did not do on purpose. Okay, but I'm glad you caught it. All right. Now I'm going to put the first law in the second law, and I get this. ds1 dE1. And which one do I want to do? I'll do delta E1 minus ds2 dE2 delta E1 is greater or equal to 0. All right, everybody see that? Yeah, everybody see where we got that minus sign from? That's because delta E1 is minus delta E2, or delta E2 is minus delta E1. And I can write this in the following way. All right, so I just pulled out the delta E1. All right. Let us pretend delta E1 is positive. So energy is going which way? From 2 to 1 or 1 to 2? Delta E1 is positive. So energy is going from 2 to 1. That's why delta E1 is growing. Which one is hotter? 2 or 1? Which one's hotter? If energy is going from 2 to 1, is 2 hotter than 1, or is 1 hotter than 2? 2 is hotter than 1. All right, so that means this thing has to be positive, right? Because a positive times a positive is greater than 0. This cannot be negative, because then we'd have a negative times a positive, and that would give me a negative. So this is positive. So we have that T2 is greater than T1, right? All right. So that suggests the following definition. 1 over T is equal to ds dE. Why 1 over T? Why not T? Well, let's say it was T. If T was equal to this, and T2 is bigger than T1, right? T2 is bigger than T1, then that would make this quantity negative, and it can't be. But if it's 1 over T, and T2 is bigger, then this quantity is smaller than this, and this is positive. Okay? So this definition, this is the definition of temperature. Definition of temperature. So this is what I call the thermodynamic definition of temperature. All right? In other words, it tells you how the entropy changes with energy, or actually the energy changes with entropy. So this is also true. And to make this more precise, the volume and the number of particles is held fixed. So that is only valid if the volume and number of particles is held fixed. Okay, so that is our definition of temperature. All right, now there are other formulas that would work as well. I could put 1 over T squared here, or 1 over T cubed, or anything like that, or some more complicated function. I don't do that for 2 reasons. Number 1, I'm lazy, so I take the simplest formula that I can think of. That's that. And number 2, it turns out that this formula works with the ideal gas law formula. It's consistent with all that. I can build my theory around that, and everything works fine. There's no contradictions. I don't need any other constants or anything. Okay, it all works there. Okay, that's fantastic. We now have a real definition of temperature. Now, I could do the same thing for pressure, and also even for number of particles. I'll just write down the answer. We're not going to use this in any way, but I'll write it down for you. Namely, the pressure over the temperature turns out to be ds dV. And there's also something called the chemical potential, and that's ds dN. So this is chemical, and I believe it works the same way. All right? So you get that by just doing the same kind of calculation that I just did for energy. In the first case, you allow the volume to move. In the second case, you allow a number of particles to go through, like a membrane. All right, but we won't need that. It's just something that I'm telling you. All right, now I do want to take this thing. All right, let's take a look at this. Imagine V is constant, no work. All right, so we know that delta E is equal to Q plus W. And if there's no work, that's equal to Q. right? That's the first law, right? But now I can see from this that if I have a little change in E, it's going to equal this little q, and I'm going to make it a dq because it's little, and that's equal to t ds, just from this. So this little dE is dq equals t ds. So this is another very useful formula. Very useful. All right. That also is pretty astounding. Think about it. We now have a way of getting at changes in entropy. The changes in entropy are related to energy moving from one system to another. And then we have that prefactor, the temperature, to go in there. So I could do this, and I can rewrite ds is equal to dq over t. And that implies delta S, a big change in entropy, would equal dq over t. In other words, I'd integrate over dq and t. And this suggests an actual experimental way of doing this. Because how do we measure energy changes due to heating or cooling? Well, we have this formula. We have something called the heat capacity. Anyone remember the definition of heat capacity? So we have heat capacity. C is just equal to delta Q over delta T. So that implies delta Q equals C delta T. Or dQ equals C dt. So now I have a way of calculating, measuring the entropy. Delta S is the integral of C dt divided by T. All right? And I can use that formula at constant pressure or constant volume. And I can get the change in entropy. Right? So this is the change in entropy. So if you give me how the heat capacity changes with temperature, I can do that. If C is constant, then we get delta S equals C, the integral from T1 to T2, dt over T. And do you remember what the integral of 1 over T is? It's the log, so we get log T2 divided by T1. All right, so there's an example of how we can compute the change in entropy. So if we do a bunch of measurements, and we measure the heat capacity as a function of temperature, so we can measure the heat capacity, measure the temperature, we can actually calculate, measure, through the measurement, we can calculate the change in entropy. So this very abstract idea of entropy that just came from this, through our analysis, through thermodynamics, we've been able to make a connection with some experimental measurements. Okay, I'm going to do one thing, and that is we can invoke the third law of thermodynamics, which says that the entropy goes to 0 at t equals 0, to write that the actual entropy is equal to the integrals from 0 to some t prime, c of t prime over t prime dt prime. All right, if s of 0 equals 0. Okay, and this is sometimes called the third law of thermodynamics. Right? In order for the third law to be valid, if you look at that, it means that the heat capacity must go to 0 at t equals 0. And we have not yet seen any formula that does that. That's why all the formulas we have do not work at absolute 0. They simply are not correct at absolute 0. Because at absolute 0, we'd have a 0 in here, and this thing would diverge. So we need to have the heat capacity go to 0 at t equals 0. We'll see some examples where that happened. So I noticed a very slight error in the last thing I wrote down. So this entropy, I want the entropy at temperature T. So the upper limit on the integral is T. I wrote T prime, which doesn't make any sense. So that's T. And this T prime here, these are what are called integration variables. I don't know if you've learned about them. But when you have two different kinds of variables, you have to separate their names. I could have used X or Y or anything for T prime. It's just a symbol that represents what I'm integrating over. All right? So it's typical to use T prime, or if you're doing X prime, etc. Okay? I don't know if you've seen that in your courses. All right. In order to make this more concrete, let's do an example. All right? So we're going to have two substances at T1 and T2, both with C of T equals C, a constant. All right? It's not too hard to do it with C not being the same for the two or even varying with temperature. But I just want to get the math as easy as possible. All right. So you bring these two together, and it's going to end up at some T final. How's that going to happen? Energy is going to flow from one to the other. There's no work done. I want you to tell me what the final temperature is. What is it? We're going to start. Which law of physics should we use first, do you think? Which law of physics should we use first? Which law of physics should we use first? The first law, right. That's what we use. So we have delta E1 plus delta E2. What's that got to equal? 0. Because there's no energy flowing outside of this. Whatever energy goes from here to here or vice versa, it's got to add up to 0. One goes up, the other goes down. How do I get the change in energy from the heat capacity and the temperatures? How do I get that? Well, this is C times T final minus T initial plus C times T final minus T2 equals 0. And the fact that they're the same capacitances, heat capacitances, means that we can use the same C there. Everybody agree? We're going to the same final temperature. Why? Why is it the same final temperature? They just like each other? Why? There's one word that is key. What's that word? Equilibrium. At equal, they go to equilibrium. Energy keeps flowing until they come to equilibrium, which means the two temperatures are the same, TF. All right, so you can find TF. I'm sure you could do this math. What do you get? All right, T1 plus T2, and I think you said over 2. All right? So that's the final temperature. All right. Now, let's compute the change in entropy for each of them. All right? So we'll do that. What is the change in entropy? Delta S1 is C. What does it say? C, the integral dt over t from T1 to T final. Everybody agree? That's the change in entropy. And we already did that integral over there. It's C log Tf over T1. Delta S2 is the same thing. C log Tf over T2. What's delta S total? Delta S1 plus delta S2. What is that? If I add this to this, what do I get? Now, if you add two logs together, what do? You multiply what's inside, right? So you get Tf squared over T1, T2. And let's put in our formula for Tf squared, for Tf. So we get C log Tf squared is T1 plus T2 squared divided by 2, so that's 4 T1 T2. Now, I want this quantity. I want to test to see whether the entropy is greater than or less than 0. What do you think it should be? What should it be? Should it be greater than 0 or less than 0? Greater. Right. That's the second law. Can you tell right away whether it's greater? What does this have to equal if it's if delta S is greater than 0? What does this have to equal? Greater than what? 1. All right, so is T1 plus T2 squared divided by 4T1 T2 greater than 1. Is that true? All right, so I'll move it over. I get T1 squared plus T2 squared plus 2 T1 T2. Is that greater than 4 T1 T2? Okay? I bring this over here, and I get T1 squared plus T2 squared minus 2 T1 T2. Is that greater than 0? Is it? Is this greater than 0? Why? Because I say so? Why? Why is that greater than 0? What is that equal to? It's equal to T1 minus T2 squared. Right? You agree that? So, anything squared, is that greater than 0? Yes. There's one case when it's equal to 0. When is that? When T1 equals T2. And that we know. So we've just shown that the entropy increases. No matter what T1 is, no matter what T2 is, it increases unless T1 equals T2. But that means it's already in equilibrium. Okay? So we've given a nice example where the entropy increases. All right? The illustration of the second law. All right. So the last thing I want to do, you might have to finish reading to get the answer. I don't know if we'll have time. But I'm going to look at different processes. We've already talked about a bunch. So we have isothermal. That means T equals constant. There's something called isobaric. That means P, pressure is constant. There's something called isochoric. Not many people use this, but V is constant. And we're going to look at quasi-static adiabatic. Quasi-static adiabatic. All right? And what that means is Q equals 0, and we're going through equilibrium states. And equilibrium states. All right. So he's either heating me or I'm heating him. That's probably quasi-static. All right. It's going through a bunch of roughly equilibrium states. All right. Thank you. Remember when the particles were over there in the corner and it filled the room? That's not quasi-static, but it is adiabatic. There's no heat coming in, no energy coming in to the room. The particle is just filling the room. So it's adiabatic, but not quasi-static. So what we're going to look at is adiabatic and quasi-static. What the quasi-static means is at each stage of the process, we can use things like the ideal gas law, because that is an equilibrium formula.